Good morning, everyone. So I'm replacing Chris Childs for this presentation. I'm going to talk about workability and retardation effects on early CSA hydration by phosphono and carboxylate chemistries. So this was a research we did while we were both in our PhD programs. He was in Carnegie Mellon, I was at Georgia Tech. And we are still processing the results, honestly. So it's an ongoing work. So CSA cements, it's one of the most promising alternatives to Portland cement. It promises like a great CO2 reductions because the limestone required to produce CSA is much lower compared to Portland cement. So the problem with CSA is that it has a really quick set time, so it sets so rapidly, and therefore we need to extend, so we need to use retarders to extend its setting time for larger scale placements. Some other quick info about CSAs. I'm sure other speakers will also give you much more detail on all these bullet points, but so it was developed in China in 1970s. Its calcination temperature is much lower compared to Portland cement, which contributes to its, this sustainability perspective. Its main phase is yeelimite, so there is no elite in CSA, in contrast to Portland cement, and it gives high early strength. So we are, when we look at retarder and CSA interactions, we consider two main mechanisms, one of which is the binding of calcium in solution. So for example, carboxylate acids can bind to calcium ions on some crystal surfaces and prevent further growth of these hydrates. Two of the most common retardants that is used in CSAs are citric acid and tartaric acid, for example. Citrate and tartarate are powerful chelators of aqueous calcium ions, as an example, and that also impacts the nucleation and growth of the hydrates. And also we have the second mechanism as the adsorption onto hydrating particles directly. So the question we ask and the challenge we try to tackle is how can we screen a diversity of retarder chemistries that are going to be suitable for CSA cements, preferably without too much experimentation. And for this purpose, we use a cheminformatics approach, which is a computational and informational technique used widely in chemistry. As an example, in pharmaceutical industry, it is used to find drugs, essentially. It's used in drug development through virtual screening. And in our case, we took this approach to relate chemical structures of retarder chemistries to predict the increase in set time in CSA cements. So this figure illustrates this cheminformatics approach. For example, from the similarity measurements point of view. So for example, you have two molecules, you encode them in certain length bit vectors, and then you look at the similarities. So for example, if two boxes have ones, so they are binary vectors. If two boxes have ones, for example, and then that means, okay, they have, for example, the same functional group in the molecule. So this leads to a similarity metric where you can use for drug development or other cases. In cheminformatics, there are fingerprint generation techniques, one of which is extended connectivity fingerprint. So that means fingerprint generation means it's representing these chemicals in these vectors, essentially. But they vary, so there are different methods. What I'm introducing here is called ECFP. So in this one, you have a vector, a binary vector. Again, this can vary in size, and you can use certain techniques to reduce the size, and it represents here, for example, in this case, we have an hydroxyl group here, and that corresponds to like a 1 in this vector. If you don't have this group, this chemical group in your molecule, then this would have been 0, and you have like a lot of these representations here. But obviously these fingerprints can can have like a huge, immense size. It can be, for example, 2,000 length in size. So this may not be very feasible for computations. So what we do is folding and filtering. So the folding is essentially setting this fingerprint length. So you optimize it. And filtering means you pick out the most important features from this molecule. So you decrease, again, the length of your vector representing the molecule, and then you can do virtual screening and set time predictions by implementing certain machine learning techniques or regression techniques, essentially. So in our case, we had to optimize. We used a technique called lasso. So you have to optimize two hyperparameters. In this case, one comes from lasso technique itself. It's alpha parameter. The second one is the vector length. So what is so in other words, fingerprint length. And you see that at this bottom right figure. On the x-axis, we have the fingerprint length, and on the y-axis, we have the minimum root mean squared error. So we looked at how different fingerprint lengths impact the error, impact the fitting, and with this analysis, we optimized the fingerprint length for our model, and then we used model in our virtual screening. We implemented across various chemistries. So we imported thousands of molecules from the PubChem depository. We implemented some constraints that should, with respect to some CSA chemistries and what's available in the market. Those are detailed more in the paper we published. So the example I'm giving here is, for example, glyphosate. We identified glyphosate as a suitable CSA because we predicted it can extend CSA set time beyond an hour. And then we tested, we validated this in the lab with Vicat measurements. Also, we did some calorimetry. We realized that Vicat set time correlated really strongly with time to main peak of heat release in CSA cements. So in this cheminformatics study, we learned that phosphono-based chemistries work really well in CSAs. What I mean is they are strong retarders. They can be strong retarders. And while screening different phosphono-based chemistries, we realized that with one chemical, so we did mini-slump experiments, and we realized that one retarder, especially PMIDA, it was phosphonometyl iminodeacetic acid, if I'm not mistaken, but don't quote me on that. So we got an anomalous plasticization by PMIDA, and we try to understand why is this happening. So in the cheminformatics study, we really couldn't have a mechanistic understanding in the retarder CSA reaction. So in this follow-up study, now we are trying to look more deeper into that. And so here are, if you want to see, here are the chemistries of these retarders that we are screening. So we have ethyluronic acid, citric acid, PMIDA, PBTCA, and ATMP. So except citric acid, they all have a phosphono-group, from 1 to 3, and they are all carboxylate chemistries. So we did set time and mini-slump experiments. As you can see, so in the figure on the left, you see set time measurements with different retarders. Set time results with different retarders. Citric acid led to the highest set time, which was maybe not very surprising. On the other hand, the ethyluronic acid, for example, didn't extend set time as much. And PMIDA was like the medium retarder in this case. However, in mini-slump retention experiments, we realized that the PMIDA is the best. From the beginning till the end, it had the highest change in spread. Until 60 minutes, we observed this, but by 90 minutes, no further spread was observed for any of the retarders. We looked at the calorimetry, the hydration kinetics here. We realized that a single peak is observed with only plain CSA around 55 minutes. So it's implying the quick set time, so in line with that. But for CSAs, including different retarders, we always observed dual peaks and more broader peaks, essentially. To understand the adsorption kinetics, we did total organic content adsorption measurements. So on the y-axis here at this figure, you have the absorption capacity. On the x-axis, we have time. So the measurements are taken at different periods. What I want you to notice here is, so the PMIDA that showed the best mini-slump retention in our experimental metrics had the lowest adsorption in the beginning. And if you may remember, citric acid and ethyl acid led to really quick set time, but they had the highest adsorption among all these retarders. And after a certain time, citric acid adsorption decreases, whereas the PMID adsorption increases. But why? So to go deeper into that, we did ICP measurements to look at the concentrations of calcium and aluminum in pore solution, as we may relate these to certain phase formations such as ettringite and aluminite. So on the left axis we have calcium concentration, on the x-axis we have time. So what I want you to notice is the citric acid and ethyl acid just corresponds to really low calcium concentration in pore solution right after like 60 minutes. It's almost none. So which may be related to ettringite formation. Maybe that is the reason for this rapid set. On the figure on the right, we have the aluminum concentration on the y-axis. On the x-axis, we have time. And again, aluminum concentration, and we see aluminum concentration increase only in plain CSA, which means, again, no retarder in this case, and in ethyluronic acid. And our current hypothesis for this is maybe the aluminite dissolution is essentially diminished here. So in conclusion, so the first conclusion, we were able to implement cheminformatics approach in the CSA cements. We identified glyphosate through virtual screening, and we predicted its set time and validated it in the lab. Second off, so screening a small library of anionic set retarders showed us that the PMIDA can give CSAs a good plasticization. And so we observed set time around 75 minutes with good mini-slump spread retention, essentially. Finally, so we are still processing our this more mechanistic results, so such as the ICP and TOC. So we would also appreciate your feedback here. But essentially, what we see here is there's like a really complex relationship between set time and CSAs and plasticization across these retarders that we used. And finally, my acknowledgement is to ARPA-E, the Advanced Research Projects Agency Energy, for funding our research projects, and in particular, Dr. Joseph King for his insightful comments. And I would like to thank you for your time and listening to me this really in the morning.